Earlier in Chapter 13, we learned how to find the mass of an object in both r squared and r cubed. In r squared, we found the mass of a lamina, which is kind of a fancy name for a plate, right? So imagine kind of a platter, but it could be any kind of shape, but it can only have two dimensions, x and y. It can't have depth. Right, so if it has density function delta of x, y, then the mass is equal to the double integral of that density function delta of x, y over the area of that lamina dA. For the solid, to find the mass, we would take the density function delta of x, y, z, but over the volume dV, and then, of course, limits of integration would be related to whatever the limits are for that solid D. All right, so knowing that, let's talk about something else, namely a moment. Now, you might have run across this in physics so far. A moment has a lot of applications in physics, and actually in statistics and probability as well. So in physics, one of the earliest ones you learn is one-dimensional rotational moments, which you know this if you've ever played on a teeter-totter or played with a lever as a kid. Me personally, I actually, when I get bored at restaurants, I'll try to balance my knife on something, right? So if I can get my knife to balance, I'm essentially playing around with the one-dimensional moment. So it's the moment is the tendency of the mass to rotate about the fulcrum. So you'll notice if you can get your knife to balance, you can kind of spin it around, right? It's because it's balancing on that fulcrum, and so it has a tendency to kind of rotate. Right, so, and you know this also from being on a teeter-totter. If you get one kid over here, right, kid of mass 2 at x2 distance from the origin, and then another kid of mass 1 at x1 distance from the origin, you can fiddle around with where the center is. And if the center is where the fulcrum is, you'll get the teeter-totter to balance. And then the kids both can have their feet dangling without touching the ground. Right? So the center of mass we call x bar. So it's the balance point. If you've ever taken statistics class, x bar you'll know has meaning in that class as well. It's the balance point, but for data, namely it's the arithmetic mean. It's the number that you get when you add up all the numbers and divide by how many there are. So a lot of people think of it as average, but it's not exactly that. So in physics, it's kind of where the center of mass is. So if you have two masses balancing, this is where they balance. And how that works is you take mass 1 times x1 minus x bar, namely the distance from x1 to x bar, and that must be equal to m2, the mass, times x2 minus x bar. And there you have it. So you have your mass times your distance, right? Your quantity times your distance, which is what a moment often is in physics. So if I wanted to solve this equation for x bar, which I could by distributing and then combining like terms, etc., I would get that x bar is equal to m1 x1 plus m2 x2 all divided by m1 plus m2. And these two terms in the numerator, those are what the one-dimensional moments are, m1 x1 and m2 x2. They're moments. Right? So we can expand upon this idea, but for two dimensions. So in two dimensions, instead of just trying to balance on a teeter-totter or a seesaw, it's the tendency of a mass to rotate around an axis. So there are two standard moments, not that there aren't more available, but these are the two most common. Namely, when you have a plate, it has a pull to rotate around the x-axis and a pull to rotate around the y-axis. So let's look at the tendency to rotate around the x-axis. That's mx, which is that second integral. Now, why is it working like that? Well, the tendency to rotate around the x-axis, right, is involving y bar, right? Because if you're rotating around the x-axis, then how far that center of mass is from that x-axis, that's a y value, right? Speaking of which, the center of mass here is x bar, y bar for this lamina, this funky plate kind of a thing that has a density. That's supposed to be a delta, sorry, delta of xy. And that density, of course, would be mass divided by area. So, kilograms per centimeter squared or something like that. So that center of mass, x bar, y bar, is where it would balance based on its density. So this y bar is that vertical distance from the x-axis to that center of mass. Well, vertical distance, y bar, but it's distance from the x-axis, right? So, but it's a y vertical distance, and so that's why you see this. mx is y times delta of xy dA. So if you want that y bar, you just take that moment, mx, and you divide it by the mass, m. Right? In other words, think of it this way. Mx is the weighted average distances from the x-axis. So it's basically saying, all the distances possible from the x-axis, what's my weighted average over the course of my surface? And of course, distance from the x-axis would be measured in y because you're going vertical. Similarly, distance from the y-axis is horizontal because you're moving to the right or to the left from that y-axis. So that's why in that integral there's an x in there. So my involves an x, and x bar would be my divided by the mass m. So my being the moment, which is the weighted average distance from the y-axis. All right, then we can expand upon this for 3 dimensions. Of course we can. So now you kind of want to think about it from your planes. So your density is delta of x, y, z. So let's think about the z-axis for just a second. If I want to know how far over this center of mass is from the or what tendency it has to rotate around the z-axis, I want to go x and y, but z is my distance, right, from the xy plane. So my xy plane is down here, and then z is the vertical distance from that xy plane. So how much does it want to rotate around that xy plane? I can determine by taking mxy and dividing it by m. And then mxy and dividing by m, and then myz dividing by m for the x bar, and so on. Right? So it's basically the same thing in 2 dimensions, but kicking it up a notch to 3. Okay, so one important use of moments is to help us find the center of mass, right, which is what we've been doing. The x bar, y bar, z bar thing. So the little bar on its head means it is the average. Okay, so just a little reminder that that denominator m is that mass that we learned how to find from earlier, either 2-dimensionally with a double integral or 3-dimensionally with a triple integral. So that was the very beginning of the previous page. So it's still there. And there are a lot of calculations that you'd have to find. So you have to find the m, and then you've got to find the myz and the mxz and so on. So it's a lot of work. But you can often use symmetry to kind of get out of some of that work because it would make things simpler. One other comment I wanted to make really quickly before I go away is that moments and centers of mass have just tons and tons and tons of applications. So let me pull up Wikipedia really quickly. So just looking at the mathematical moments, you can see there's a whole bunch about the significance of it, and there's different, this is my field of study for one of my master's degrees, which is statistics and probability. There's a whole bunch of relationships there, et cetera, et cetera. And then that's not even talking about the physics applications of it, which there are plenty of them, including torque, which we already learned about. Torque is a moment, and related to a moment. Centers of mass, you can see, is the first moment, mass normalized by the total mass. So that's what we were just doing. You take your integral. We're doing it for a continuous distribution, so we're doing it right here. So you take your integral and then you divide it by your mass. That's what they're telling us right there. So then you have your moments of inertia, your moments of angular momentum, your moments of plasma moments. That sounds exciting. Area moments, also thrilling. So magnetic moments has to do with dipole, measuring the strength and direction of magnetic sources. So you can see that these must have a lot of applications, and they do. And that's just mathematics and physics. There are other applications as well in different fields of study. So moments are actually a very important concept, and we're just kind of touching on them here.